Hello. Today we're going to talk about how to derive the equations of kinematics at constant acceleration. They are on the screen right now. V equals V naught plus AT. X minus X naught is 1/2 V plus V naught times T. X is 1/2 AT squared plus V naught T plus X naught. And V squared minus V naught squared equals 2A times X minus X naught. Now, in these equations, we will only be working in one dimension, so x will be our displacement. It will be only back and forth. Single vector component, only x, no y or z. V is velocity, which is the change in displacement over change in time. X is displacement. By definition is displacement. Okay, excuse my handwriting. V is velocity, which is the rate of change of displacement, how fast something is going. And that can be positive or negative as a vector quantity like displacement. And acceleration is the rate of change of velocity. Now, the symbol naught, the little zero symbol, x naught or v naught, that simply is what that quantity will be at t equals 0. Okay? So the starting point, the starting position, and the starting velocity, that's what x naught and v naught mean. Again, look at the equations. Let's look at number 1. But first, let's go over something to make this clear. Let's say that x is 5t cubed minus 4t squared plus 7t plus 3. Let's review. Let's say we want to find v. Velocity is the rate of change of displacement, which is the derivative. Let's review from your math class how we take the power rule for derivatives. We have a power of t. If we take the derivative with respect to t, we have to use the power rule. The derivative of a t to the n, okay, with respect to t, that's going to change with respect to t, is this, n a to the t minus 1. a to the tn minus 1, sorry, tn minus 1, like that, okay? So by applying that formula, we get this 3 goes down here, this becomes 15, 3 times 5 is 15, t squared. This 2 comes down here. Now, here we just have a power of t. If we make n as 1, the 1 comes down here, and 1 minus 1 is 0. T to the 0 power is just 1. So this is just 1 times 7, which is 7, times t to the 0, which is 1, is redundant. Now, 3 is a constant. What's the derivative of a constant? And a constant, nothing changes, so its derivative is 0, and so that's redundant. Okay? Now let's find the acceleration. Three comes down here. We have 45. This is t squared. Make a mistake here. Or sorry, oops, did this wrong. Made a mistake. That was t squared, not t cubed. So 2 times 15 is 30. T is 8. Now, x naught, okay, is going to be x of 0 so we stick 0 in for t. This is 5, 0 cubed is 0, minus 4, 0 squared, also 0. 7 times 0 is 0, we're left with 3. And v naught again, we put 0 in for t. 15 times 0 squared is 0, minus 8 times 0 is 0, and v naught is 7. Okay? Doesn't matter what the units are. The units are arbitrary. We can call this x displacement meters, v is meters per second, and a is meters per second squared. Now here we have a is 30t minus 8. The acceleration here is not constant. So the equations that I just showed you don't apply. And the problems we're going to talk about are actually going to be simpler than this. Now let's move on. We know that if a acceleration is dv over dt, v okay, is the integration, the antiderivative, of a with respect to t. Now let's see what we have here. We have a dt and by the fundamental theorem of calculus, the integration of a derivative is the function side, so that's just v. And so we take this integral here, we have at plus an arbitrary constant is v. Now, we know that v of 0 is v naught. So v naught is c plus a times 0, which is 0. So c, the arbitrary constant, is v naught, is the initial value of the velocity. So we have v is at plus v naught And if we look here, that is equation 1. Now, let's look at equation 2. Oh, no, not equation 2, equation 3. Let's derive equation 3. We know that V is AT plus V naught. What happens when we integrate both of these with respect to t? dt here, dt. If V is dx over dt, the integration of v with respect to t is x. Again, by the power rule for antiderivatives, we're going backwards. So this is going to be the integration of b t to the n dt is going to give b e to the n plus 1 over n plus 1. That's the power rule for the antidifferentiation, and plus the arbitrary constant c. When we do this, we have a t squared over 2. Again, a is a constant. So this is just a t squared over 2 plus v naught t and again an arbitrary constant c. Now what is that arbitrary constant? X of 0 is of course x naught. So we put 0 in for t here. We have 8 times 0 squared over 2. That's 0. That goes away. V naught times 0, whatever it is, that goes away. And we have c equals x naught. One half a t squared plus v naught t plus x naught. And if we look here, that is equation 3. Now, let's clear this. This one might be a little tricky. We're going to talk about equation 4, right? We know that a is dv over dt. Now I'm going to split the differential. dv over dt is dv over dx times dx over dt. I can still do this even though I am using differentials. These are not zero, they're infinitesimally small. This is the same thing as A over C equals A over B times B over C. Okay? So we have A is dV over dx times dx over dt. But what is dx over dt? It's just v. This is just v. A dx times v. Now we can move this dx over here. A dx equals v dv. Integrating both sides. Now a is a constant, so it goes outside the integral. So the integration of a dx is just ax. And this, by the power rule, is v squared over 2 plus the arbitrary constant c. Now, what's this arbitrary constant? We know at t equals 0, even though time is not this equation, we know that at t equals 0, x naught is going to be, x is going to be x naught, and v is going to be v naught. So let's go back here. Let's erase some of this here. Solving for c, we have a x naught equals v naught squared over 2 plus c. And these are all constants. A is a constant, and of course x naught and v naught are also constants, so this is just numbers at this point. Nothing's changing. And this is a x x naught minus v naught squared over 2. Okay? Now we plug this back in into this equation here. C, ax equals v squared over 2 plus c, which is going to be plus c, which is a x naught minus v naught squared over 2. And we can rearrange this, so this is going to be a x minus x naught equals v squared minus v naught squared all over 2. Okay? And we can just multiply both sides by 2, move this over here, and we have equation 4. Now equation 2, we know that a, now let's look at equation 4. We know that a is a constant and it's change in velocity over change in time. So we have a is v minus v naught over t. We plug this into equation 4. We have 2 v minus v naught over t, which equals v squared minus v naught squared. And v squared minus v naught squared, the difference of 2 squares. So that can be turned into v plus v naught v minus v naught. Okay? Now, let's look at this. V minus v naught cancels out from both sides. Okay? Oh, sorry, x here. Okay, x here. So what we have is x equals, sorry, x minus, mistake here, this is x minus x naught from equation 4. T over 2 goes here, we have x naught. We're going to multiply both sides by t over 2. Times v plus v naught. And with that step, we have equation 2. That's how you derive the equations of kinematics for one dimension at constant acceleration.